Okay, this is 6.3, exploring graphs of the primary trigonometric ratios. So, it's a little bit of a review today, but it's a dense review, and what I mean by that is there's a lot to kind of remember. So explore the math here. Somebody mind reading? Volunteer. It's a long paragraph. I get to pick. Luke, you can see it right off the board.
Sorry, I'm just grabbing it. Sorry. The unit circle is a circle that is centered at the origin of the radius of 1 unit. On the unit circle, the sine and cosine functions take a particularly simple form. Sine theta equals y over 1 equals y, and cos theta equals x over 1 equals x. The value of sine theta is the y coordinate of each point on the circle, and the value of the cos theta is the x coordinate. As a result, each point on the circle can be represented by the ordered pair xy equals cos theta sine theta, where theta is the angle formed between the positive x-axis and the terminal arm of the angle that passes through each point. For example, the point cos pi over 6 and sine pi over 6 lies on the terminal arm of the angle pi over 6. Evaluating each trigonometric expression using the special triangles result in the ordered pair root 3 over 2, 1 over 2. Repeating this process for other angles between 0 and 2 pi result in the following diagram.
Okay, good. So here's the basic, very simple unit circle, and we're going to look at the a little closer at the more complex one. But here's the basic idea. So your theta angle is drawn between the positive x-axis. Your radius, of course, is 1 because it's a unit circle. And as a result of that, your sine theta, which we know as opposite over hypotenuse, becomes actually just the y value over 1. So this is a little bit of a review from yesterday where we translated the radius into the hypotenuse and then opposite into y and adjacent into x. So it's the same idea here. Any questions so far? Anybody here has never seen the unit circle or doesn't remember any of it? Nailed? And Anthony? Okay, this is going to be pretty heavy for you guys, I'm not going to lie. You're going to have to try and pay attention as best you can because there's kind of a lot to the unit circle, as you're going to see in a minute. If you don't remember exactly, or after today's lesson you still don't know, you might want to go onto YouTube and just look up unit circle. There's a bunch of decent videos on it. Okay, here it is in all of its glory. So we have both the radian measured degrees as well as the degree angles here. So 30 degrees we know is pi over 6, 45 is pi over 4, and 60 is pi over 3. So these angles also you should know, generally speaking, even just how to draw, right? We know this is a 30-degree angle here. 45 splits the 90 in half, and 60 is a little past the midway point between the 90. Okay? You'll also notice that the points on these end terminal arms, these points, there's a pattern here. Okay, so all of them are over 2. Okay, so, and you'll notice when we go from 30 degrees, the x value is larger than the y value, right? Because we're going all the way over here to almost the end of the circle, and the y value we're going up just halfway. Okay, so that makes sense that the x value would be more. So notice how this pattern goes. It goes root 3 over 2, root 2 over 2, root 1 over 2. You know, root 1 is just 1. Okay, so there's a pattern there, 3, 2, 1. And then the same thing in the y values now, but in the opposite direction. 1 over 2, or root 1 over 2, root 2 over 2, and root 3 over 2. So these values here, you should be able to memorize. It's just 1, 2, 3, right? It's all over 2, where the numerator is rooted, right? So root 3, root 2, root 1, root 3, root 2, root 1, all over 2, everything over 2. So these values now, these x and y values, so are very easily to identify and to remember. Arguably easier than creating the special triangles, right? If you can remember that pattern, if you can draw this unit circle with this representation of 30, 45, and 90 degrees, you should know very quickly the exact values of sine 30, cos 30, sine 45, cos 45, sine 60, cos 60, right? Just set it up like this, put in your values, 3, 2, 1, 3, 2, 1 the other way, and now we can figure those values out, right? So if I were to ask you, what's the value of sine 45? Who can tell me? Hands should be flying up, right? Sine 45, yeah. Yeah, root 2 over 2. Here, it's the y value of this angle, 45. So, Daniel, if I said cos 30.
It would be 1 over 2.
No, that's the y value. That's sine of 30. You're close. That's the y value, right? Because here's 30, Daniel. And you told me 1 over 2, which is the y coordinate. It's the y point. So not 1 over 2, but?
Just 1?
No. It's easier than you're thinking, yeah. Yeah, root 3 over 2, right here. Okay? This is the x value here. Okay? So if I were to ask sine 60, Naod,
Sine root 3 over 2.
yeah, root 3 over 2, right here. Sine 60 and cos 30, we know from special triangles, is the same, right? Root 3 over 2 and root 3 over 2. So very, very quickly, if you're able to draw this and remember root 1, root 2, root 3, root 1, root 2, root 3, all over 2, you can create this circle and get these values very quickly. Yeah, 10, so we're going to cover tan in this lesson, but as we know, tan, it's just sine over cos theta. So if I said tan 45 degrees, that would be this value, root 2 over 2 over root 2 over 2, which is 1. If I said tan 60, Luigi, what's tan 60?
Would be 1 over 2 over root 3 over 2.
No, the other way, right? Yeah, root 3 over 2 over 1 over 2. Okay, and then when you divide by a fraction, you actually multiply by the reciprocal, right? Okay, so tan 60 is root 3. So now if I said to somebody, what is, and now we're working with radians here, Nicholas, I said, what is cos pi over 6?
Cos pi over 6?
Yeah.
It would be 1 over 2?
Nope. Close.
Okay, 3 over 2?
Yeah, root 3 over 2. Because cos, remember, is the x, right? And sine is the y. Okay? Y is sine the y and cos the x? Well, we can see right here. If this is theta here, sine is opposite. So sine is going to be this side over the radius of 1. Cos is going to be the adjacent, so it's going to be this length. Okay? Elijah, if I said sine pi over 4. Right, root 2 over 2. If I said, Luke, sine pi over 3.
Sine pi over 3 would be 2? No.
Sine pi over 3.
3 over, root 3 over 2.
Right, this value. So the y coordinate of that value. Okay, everybody understand that? Any questions about that? That's very important. That's why, but way back in grade 10, I showed everybody how to draw this, and we can actually get values of any degree. Okay, we said, 145. What is the sine of the angle 145? Or sorry, 135. So we go to 135, which is here. We can see it here. In radians, it's known as 3 pi over 4. And we want to find sine, so that's going to be the y component. Again, it's going to be positive root 2 over 2. Okay? And that's how we also know that all of these signs stay the same, right? Cast. So all the cosine values, or all the x values here, are positive. 1/2 is positive, root 2 over 2 is positive, root 3 over 2 is positive. Okay? All of the sine values in this quadrant here are below the x-axis, so they're negative. So all of these values are negative. Okay, Marco?
So where do you start counting the quadrants? From C or A?
From A. This is quadrant 1, 2, 3, 4. Okay? It's the same way you would count the way you count angles. Okay, angles go this way. Okay, yeah, Luigi?
Wouldn't it be better to be ASTC instead of cast?
It doesn't sound as good.
Well, sir, it does.
Yeah.
ASTC.
Say you're acting.
No, I can't say it on video.
Yeah, there's a lot of things that do that, right? Like I argued about that a squared plus b squared equals c squared.
Yeah.
It should be s1 squared plus s2 squared equals h squared,
Oh, so there's a
but it
good
doesn't
acronym
sound
to
as good.
There's a good acronym to remember this.
All slugs.
I like cast. All right. You can think of one, Luigi. Tell us tomorrow.
Okay.
So what do the graphs of the primary trigonometric functions look like when theta is expressed in radians? So we should have an idea already about this, right? You guys, as a review, you guys know this much, right? This is y equals sine x, y equals cos x looks like this. Okay? This should be, you know, big time review for you guys. And then
Sine x is starting at 0.
yep. And then tan x. You guys haven't done tan x yet?
No.
Okay, we're gonna do it today. Looks like this. We got some great vertical asymptotes there. Okay. So that's what they look like generally speaking, and this was before it was 360, right? Now what are we gonna call it?
2 pi.
Yeah, this is gonna be 2 pi. So where this was 180 before, it's gonna be pi. And that's the only difference, really.
I gotta get this 3
All right. All right, the first question says, copy the following table, complete the table using a calculator and the unit circles shown to approximate each value to 2 decimal places. So we can, if we do this on a calculator, what do we have to be careful about if we go to do this on a calculator? What's one of the things we want to be aware of before we start punching this into our calculator?
The mode has to be radian.
Good. The mode has to be radians, okay? And I said that yesterday. If you're working with pi, you have to be in radians, okay? Because in actual reality, if this was in degrees, you would be taking the sine of 3.14 divided by 6. So it would be the sine of 0.5. The angle 0.5, sine of the angle 0.5, which would be 0 almost, right? It'd be really, really small. Okay, if you can imagine drawing an angle at 0.5, it's going to be this angle in here. The sine value is going to be here, tiny. That doesn't work. That's if you're in degrees. And all of these values would be super small then, if we were in degrees. You have to make sure you're in radians when you're working with the value of pi. If you're in degrees, what would this angle be? What would you convert the pi to if your calculator's in degrees? This pi would not be 3.814. It would be what? Come on, guys, all of yesterday. Yeah, 180, right. You'd have to say that this would be 180 divided by 6. Okay, so if you kept your calculator in degrees, you would have to make each pi here 180. All right. So some of these values we should know, right? We should know right off the bat. So sine 0. So here's 0. What is the y component of the angle 0 here? Right? What is the y component of this? It's 0, right? Okay, we also get that from the graph. What is the value? Remember, this is theta over here. What's the value of sine when theta is 0? It's 0. Okay, sorry, this is theta down here, and this is sine x up here. All right, next one. Pi over 6. So we can look at our unit circles, see pi over 6, and find the sine value here. It's a half. Pi over 4, sine value, root 2 over 2. Pi over 3, sine value, root 3 over 2.
So your sine value is the y value?
Yes. Pi over 2, which is 90 degrees, sine value is going to be 1.
Okay.
2 pi over 3, which is over here, the sine value is going to be root 3 over 2.
Bit much to take in.
Root 3 over 2 over 4, the sine value here is going to be root 2 over 2. Okay, etc.
So wouldn't that be 1? Root 2 over 2?
No. If we're dealing with the cos value now, what is the cos value at 0 degrees? It's 1. The cos value at 30 is root 3 over 2. Root 2 over 2. 1/2. And 0, yep. Okay, so here's the completed chart. I'm going to hold it there for a minute just so it's on the video. I won't bother writing them in. But again, all of these values, either you could have got right from the unit circle here, just by reading off these coordinates, again, x for cos, y for sine, for the respective angles, or you could have got them with your calculator, making sure your calculator was in radians, if you're using pi as 3.14. Okay, and you get all these decimal values for the different values of cos and sine. Yeah. Sorry? No idea. Maybe it's just easier to write in the box. No idea. I think the point, I guess, was to verify your calculator values with the fraction values from the unit circle. Okay, that's what I would guess. All right.
So how would you like us to put in like a decimal value or fraction?
I always prefer fraction form if you know the fraction form because it's exact. Any other questions about this? These values. All right. Next, it says plot the ordered pairs theta, sine theta, and sketch the graph of the function y equals sine theta. On the same pair of axes, plot the ordered pair theta, cos theta, and sketch the graph of the function. So all we're doing now is plotting the angle on the x-axis and the sine theta on the y. Okay? So that's all this is here. We've taken this value here, 0 and 0, and plotted 0. So this dark line here is this row plotted with this row. Okay, so pi over 6, or if we just go to the big ones, pi over 2 is 1. So pi over 2 is right here. Again, this is pi and this is 2 pi, so pi over 2, or half of pi, is right here, and the value is 1. Okay, so we're just taking this point, this being x, y, x, y, x, y, x, y, x, y, x, y, and plotting them on the black graph. And on the gray graph here, it's cos theta versus theta. Okay, so we're taking this point 1 and 0, 0 being the x value and 1 being the y value. Okay, 0 and pi over 2, 0 and pi over 2 is here. Any questions with these two graphs? And what we notice is we get those graphs that I drew at the very beginning. The black one, of course, being y equals sine theta, and the gray one here, y equals cos theta. Any questions? Okay, so we have our two graphs there. It says state the domain, range, amplitude, and equation of the axis and period of each function. All right, so domain and range. For both of these, I think it's easy to see that the domain is going to be theta, all real numbers. Okay, remember, this is not x, they've plotted it as theta. Okay, so your domain here is going to be theta ER. Okay, I think that's pretty self-explanatory. The range is between -1 and 1. So our range is y is greater than and equal to -1, and it's less than and equal to 1. Okay? And it's equal because it actually does touch that point of 1. The amplitude is 1. Remember, the amplitude is the distance from the center of the graph to the top. Okay? Or the max minus the min divided by 2. Or max plus min divided by 2. Okay, that's our amplitude, so 1. From 0 to the top, that's 1. The equation of the axis is y equals 0. That's the equation or the y value of the center of the axis. So if we translate, that axis will move up and down in the middle of the function. Okay, in this case, it's right cut through the middle on the x-axis, so the equation of the axis is y equals 0. Any questions about any of those? And the period is 2 pi. That's the amount of x value it takes to start repeating itself. Okay, once we get back to 2 pi here, the function is going to just repeat itself over and over. So that's our period. Again, all of that is review. Any questions? All right. D, so now we're getting into something new. Recall that tan theta is equal to sine theta over cos theta. Use the values from your table for part A to calculate the values of tan theta. Use a calculator to confirm your results to 2 decimal places. So, sine theta over cos theta for 0.
0.
We would take this value, sine, so it would be 0 over 1, which is just 0. Okay? The next value, we'd have 1/2 over root 3 over 2. Yeah, so it ends up being 1 over root 3. Okay, and you would take your calculator and just verify that those answers are in fact right. Okay, we end up with this table here. Notice the areas where it's undefined. This is where cosine, which is of course on the denominator, right? Tan theta is equal to sine theta over cos theta. This is when cos theta was 0. So at 90, cos theta was 0. We're going to get undefined values here. So what happens on our graph of tan theta? Yeah, we get a vertical asymptote. Okay? The other areas where it's 0, that's when our sine value was 0, because 0 divided by any number is still 0. Okay, so at theta, our sine value over here was 0. Okay, so our tan value is also 0. At theta over 2 here, our cos value is 0, so we're doing 1 divided by 0, which is undefined. So that's why we get an undefined value there. Any questions with that? All right, that's D. E, what do you notice about the value of the tangent ratio when cos theta equals 0? What do you notice about the value when sine theta equals 0? So that's what we just spoke about. When sine theta equals 0, tan theta is 0. When cos theta equals 0, tan theta is undefined. Based on your observations in part E, what characteristics does this imply on the graph? We talked about that. So vertical asymptote where cos theta is equal to 0. G, what do you notice about the value of the tangent ratio when theta is equal to plus or minus this, this, this? Why does this occur? So this occurs because of the formula sine theta over cos theta. So what we notice about these values is that they're the values of sine over cos. That was the whole point of that exercise, was to make the divisions and then verify with your calculator that they are the same values.
Wait, what happened? Sir,
Yeah.
what happened when...
What do you notice about the value of the tangent ratio? When theta is equal to these values, we notice that the value of the tangent ratio is equal to the sine value over the cos value of those same ratios. Okay? Actually, in each one of these cases, I believe they're variations of 45 degrees. Yeah, sorry. So in each case, the tan ratio would be 1. Okay, and that's because it's sine over cos, so they're the same values in each one of these. Right, so if we go back to here, we look at theta over 4. See how they're the same value? So tan's going to be 1. You see that? If we go over to 3 theta over 4, 3 theta over 4, see they're the same value? So tan here will be negative 1. Okay? All right. On a new pair of axes, plot the ordered pairs theta, tan theta, and sketch the graph of the function. So now, all we're doing is taking these table of values that we figured out in D, theta and tan theta, and we're just plotting them. So again, x and y values, and we get this graph. So this is our tan theta graph. And what you'll notice is there's a vertical asymptote right here at theta over 2 and 3 theta over 2. Okay. Alright, determine the domain, range, amplitude, equation of the axis, and period of this function if possible. So, the domain. So we have to look at all the vertical asymptote values and say that x cannot be that value, or theta in this case cannot be that value. So theta are all real numbers where theta cannot equal pi over 2, which makes sense. Plus, and it shouldn't have been 2n pi here, it should have just been n pi, where n is integers increasing from 0, right? So if n is 0, then this is just pi over 2, which is here. If n is 1, we get pi over 2 plus pi, so we would get 3 pi over 2, which is here. If n is 2, we would get pi over 2 plus 2 pi, so we'd have the next one, which is over here. Okay? And likewise, when n is negative values, we can also go and it's repeated, so we get vertical asymptotes. Okay? Does everyone understand how this equation works? Okay, I'm going to repeat it one more time. So, everyone understand why pi cannot equal pi over 2?
Yes.
Okay, so there's a vertical asymptote there. So now, we want to develop an equation where we don't have to list all of these individually, right? Because you know how this is going to be repeated, right? So it's going to be every pi value, there's going to be a vertical asymptote. Does everyone understand that?
Yeah.
So the actual values where the vertical asymptotes will be pi over 2, 3 pi over 2. I'm just adding a pi each time, right? 5 pi over 2, 7 pi over 2.
You're adding 2 pies.
No, because it's divided by 2, I'm just adding a pi.
Yeah.
So I'm not adding 2 pi, I'm adding a pi each time.
Yeah, because that pi is a 2.
But you're keeping the 2 there as well.
Yeah, because,
2 is the whole.
Okay.
so this is 0.5 pi, right? This is 1.5 pi. This is 2.5 pi. This is 3.5 pi. You get it? You got it? Everybody get it? All right, so now I want to express this in a much more simple way than writing, you know, pi ER, pi cannot equal this, or this, or this. Okay, so that's what this equation is trying to do. So let's just explain that for a second. So n can be any integer. Remember, integers are whole numbers, right, including 0. So for the first one, if n is 0, pi cannot equal pi over 2. So we get the first one. Make sense? Right? When n is 0, we get the first one, right? Because this whole term goes away. Okay? When n is 1 now, and they used to have a 2 here and I erased it because it was wrong. Okay? Shouldn't.
N pi.
Sorry?
It's just n pi.
It's just n pi, yes. Okay? When n is 1 now, we're going to get pi over 2 plus 1 pi, which is half a pi plus a pi, 3 over 2 pi, right? When n is 2 now, we're going to get pi over 2 plus 2 pi, which will give us 2.5 pi. Make sense? Okay, everyone understand this equation now? Okay. The range, of course, is YER because we cover all values of y. Going down, and coming up.
So
Okay?
So just especially writing the I, because you know with the R we have like a double strand in the R. But in the I,
No, it's just an I like that. Integer. Okay? There's no amplitude or an equation of an axis. That's why is there no amplitude? Because the amplitude is, it's in infinity here. There's no kind of up or down, and there's no equation of axis because it's not a sinusoidal or cosinusoidal curve. Okay? So that's why those don't exist. All right, let's look at the reflecting. The tangent function is directly related to the slope of the line segment that joins the origin to each point on the unit circle. Explain why. Why is the tangent related to the slope of the line? So here's our unit circle, right? Here's our theta. This point here is, of course, sorry, thanks. This point here is cos theta sine theta. So tan is sine theta over cos theta, which is, if this is 0, 0, it's going to be rise over run, right? So tan theta is the slope of this line. Okay? This is one point, and this is the other point, 0, 0. So if you do y2 minus y1, x2 minus x1, that's our slope, right? y1 and x1 are both 0. So it's actually just sine theta over cos theta, okay? That's why it's related to the slope. All right. Where the vertical asymptotes for the tangent graph located when between 0 and 2 pi, and what are their equations? Explain why. Sorry, where are the vertical asymptotes for the tangent graph located? Okay, we went over this already, right? They're located at pi over 2, 3 pi over 2, 5 pi over 2. And why are they found at this location? Because cos theta is equal to 0. That's why. That makes the tan theta undefined. How does the period of the tangent function compare with the period of the sine and the cosine functions? Who can tell me? What is the period? First of all, what is the period of the sine and the cosine functions here?
2 pi.
Right, 2 pi. Why? Because it takes 2 pi to go through one complete revolution before we start repeating. So period is equal to 2 pi. This is for cos and sine. What's the period for tan theta?
wait,
Yep.
no, it's
No.
is it pi over 2 plus
No.
pi?
Anyone else?
Just there is
Yeah, Luke?
just pi.
Yeah, it's pi, right? Because from here to here, see how it's the exact same point there and there? It's going to go up, right? It's going to go up. So from there to there is pi. That's the period. That's the amount of time or x value it takes to start repeating itself.
Okay.
Okay? You can also see it from here, right? This is the complete function right there. And it's pi, the period from there to there. You see it, Elijah? So it's pi. That's probably why this 2 is here, because typically they use 2n pi for the sine and the cosine, right? Functions. But just for tan, it's just pi. That's probably the mistake they made. All right. Summary. So the graphs of the primary trigonometric functions can be summarized as follows. So this is the exact same graph we learned before with degrees. Now we're just putting in radians. Okay, so where it was crossing here at 180, it's crossing at pi. Where it was ending at 360, it's ending at 2 pi. You guys remember the speech? Did I give the speech in grade 10 on tau?
Yeah.
You guys remember that? Pi or tau?
Yeah.
Here's where it comes into play. Okay, I think I mentioned this. In grade 12, it would be maybe a little more interesting to you. If we were using tau instead of pi here, this one revolution would be 1 tau. Half a revolution would be half a tau. We wouldn't have to keep dividing by an extra 2.
What's tau?
Tau's 2 pi.
So why don't we just use
It's a very good question. Many of the leading mathematicians now are trying to translate education to stop using pi and use tau instead.
What does tau look like?
Tau looks like this.
The real question is, it
Oh, that looks more complicated.
looks like a pie with
Yeah.
More complicated.
So is there any math where you use tau instead of pi?
Look up on YouTube pi versus tau. Very interesting videos.
On the channel.
Yeah, but so why do they always use these like Asian names?
I think they actually originate. It's a Greek alphabet, no? Isn't it? Delta, gamma, theta,
Theta is Greek.
beta. Yeah, it's all Greek. And I guess probably because the Greeks were the originators of a lot of the math we're doing, right? Is it?
Yeah, I thought it was a use.
I don't know. I thought it was an O.
Wait, so instead of pi, it's called tau?
Yeah, tau is equal to 2 pi.
Oh, okay, so it's
Okay, next one. Here's our cos graph. Again, it's identical to how we remember it with degrees. It starts off at 1 and it goes back up to 1 over the course of 2 pi or 360 degrees. Here's our characteristics, our period. We should know all this stuff, right? Period's 2 pi, axis is y equals 0, amplitude's 1, max value 1, minimum value -1. There's your domain and there's your range. And they're identical, right? For sine and cosine. Finally, our new graph looks very complicated when we look at it in this many periods of it. Okay? But we should understand it now a little bit more. You can see that the period is only pi. So it's going from one point to the exact same point. The distance is pi. The axis is y equals 0. So that's just the center. Not sure why that's there. Amplitude is undefined because it's infinite here. There's no max or minimum value, and the vertical asymptotes are here.